Most people don't know this, but I've also got a second channel. And on the second channel, I've been posting for the past 8 months videos on a special project that I've been working on that is loosely related to school. This project started out as a frame buffer test that ran on a Pi Pico and has now turned into what I like to call the Cluatron. The Cluatron is a programmable microcomputer with integrated command line and program editor. Inspired by machines like the Amiga, the Commodore, the MSX, but also the Gigatron, the Commander X16, the Column Maximite 2 and Picomite, and the fancy console Pico 8. What I want out of similar boards is a better scripting language that isn't BASIC, because BASIC is not really that good and kind of dated these days. A more contemporary input method, so not like a proprietary serial controller / keyboard that's connected to the machine. I also want to have affordable hardware, so I didn't want to have like an unnecessary amount of parts to provide basic functionalities to the machine, so not like the Commander X16 or like an MSX. I also wanted to have the ability for software to be programmed on the computer itself, which is an issue the Gigatron has because you can't really program any proper software on that machine, unless you want to make a script inside of Tiny Basic. And I also want to have better hardware interaction from the scripting language, which is something I'm kind of missing from Pico 8. The current big features of the Cluatron are to start off with the video. The video is 15-bit VGA with index color palette at a resolution of 320 by 240, which means it's a quarter of the actual VGA standard. And index means that it basically, of those 15-bit VGA, it only uses 4 bits per pixel, which means you can have 16 different colors at the same time on the screen. There's also support for 4 USB devices at the same time, thanks to a USB hub. Keyboard and mouse are right now supported, but in the future I also want to support gamepads and maybe even USB sticks, if possible. Or perhaps maybe in the future also USB serial devices, like an Arduino, so you can read out serial data from an Arduino on the Cluatron. The crowning feature of the Cluatron is the modified Lua interpreter, with integrated commands for reading out certain USB devices and writing data to the screen. It also contains all of the Lua libraries, like the math library and the debug library. To interact with the modified Lua interpreter, a programming shell has been devised. Commands written in the programming shell can only be 79 characters long. This might be a limitation, but you're also able to call back past commands sent with the arrow up and arrow down key. If you want to have programs that are longer than 79 characters long, there's also the program editor, which is currently quite bare bones at the moment, but it does allow for programs till a size of 32,767 characters long. Switching between the shell and the program editor is done using the F1 and F2 key. F1 for the shell and F2 for the program editor. In the future there will probably be more editors for like sprites or sound, and these will have F3 or F4 in the future. The hardware is currently based off a Raspberry Pi Pico, which has the RP2040 MCU on its board, which has dual-core ARM M0 Plus cores, 264 KB of static RAM, USB host and device capabilities, and programmable I/O capabilities. It also has a clock chip that is tied to a phase lock loop, which means you can overclock the device, and in the case of the Cluatron it's currently clocked at 250 MHz, which is the max clock frequency to use on the RP2040. It used to be 200 MHz, but I managed to overclock it to 250 after I resolved a certain bug that I will come back on later. For storage of the operating system, a QSPI memory chip is currently used, with 2 MB of storage. This can be increased to 16 MB of QSPI flash memory. For video generation of the VGA signal, a resistor array has been used. In this case 15 resistors, 5 for each color channel, each having a value of somewhere around the value of 500, 1000, 2000, 4000 and 8000, which allow for 33,768 different colors. These resistors are directly connected to the I/O channels of the Pi Pico. You might be hearing me listing all of these features and hardware and probably are wondering why I have made these choices. That's what I want to go to in this part of the video. First off, why the limited colors? As I've said before, the Cluatron is capable of displaying 16 colors simultaneously. This might seem limited considering the resolution and the amount of different colors that are possible on the machine. Whatever is displayed on the Cluatron is decided by the frame buffer. This frame buffer is an area of memory where all of the pixel values are stored. And in the case of the Cluatron we have 320 by 240 pixels, which comes down to 76,800 pixels. If we wanted to have a frame buffer of 320 by 240 with 15-bit pixel depth, we would require a 16-bit U-integer array, meaning each pixel stored will cost 2 bytes, which would cost 154 kilobytes of memory. That is around 60% of the whole system memory of a RP2040 chip. That's just an unnecessary amount of memory for just a frame buffer. That's why I chose for an option where you would only need 4 bits per pixel, meaning I have an array where each byte stores 2 pixel values. In this 4-bit system, each pixel is mapped to an actual color value, that is a 15-bit value, which is done using a lookup table. If you counted the memory size of the frame buffer, that's 4 bits per pixel, and the lookup table, you would come to a memory size of only 40 kilobytes of RAM, meaning this system only takes up 15% of the whole system memory of the RP2040 chip. The best part is that the user is not limited to the colors seen on the screen, since the colors can be changed using commands, which I think is a pretty decent trade-off. Another choice I feel the need to justify is why I've chosen the RP2040 chip. This chip was chosen because I found it affordable, accessible, reliable, to have a sufficient amount of RAM, it's also fast, and it's also dual core. The only thing I'm missing about the RP2040 is the amount of I/O pins. This is why I'm also looking into replacing the RP2040 chip with a RP2350B chip, which is a chip similarly used on the Pi Pico 2, but with more I/O pins. The B stands for more I/O pins. The RP2350B also has more up speed and better cores, and double the amount of RAM, but that will also mean that this chip will cost far more than the RP2040. Another choice I felt the need to justify was the choice of using an interpreter over a compiler. If I want to have a compiler to work, I would also have to create some sort of kernel. Kernel development is of course one of the hardest things in computer science there is, since you would also need a way to execute this native machine code. Having a program that turns your written code into machine code is also quite compute intensive. This also comes with the added disadvantage of having it hard to debug. That's why I've chosen for Lua. Since Lua is closely mapped to the C code it executes, and Lua is easier to embed and costs less ROM and RAM space. The last thing I want to explain was the name, Cluatron. Clua because Lua, and Lua is the scripting language of the OS, and the OS is written in C, so Clua. Initially I want to use a Q for Cluatron, but I discovered there was an app on the Play Store that was named Clua, so I switched the Q for a C. Tron is a tribute to different machines ending on Tron, like the Gigatron, the Cyclotron or the Magnetron. Something else I felt the need to talk about are the biggest development struggles I've had so far. The first issue has something to do with floating point functions. As soon as I want to execute a function where a float was one of the parameters, the entire system would freeze up. This was during development one of the longest prevailing errors. Seemingly every function of the Lua math library was broken. I tried to remedy this by making my own custom math functions. These would also break on execution. So this meant that it didn't have to do anything with the Lua codebase. So I started to look further. Then I discovered the RP2040 doesn't have a native FPU or floating point unit inside of its silicon. This meant that every floating point operation was done in software. And let there now be 2 different floating point units in software that can be done with the Pi Pico. The first one is based on the Pi Pico boot ROM, which is also the fastest and the default. And there was also the compiler version, which is described in the documentation as a soft floating point implementation. As soon as I switched to this implementation, I was finally able to use floating point functions again with the Lua interpreter, which meant that all of the math library functions finally worked, and I was also able to use the math.py number. Another issue that became more and more apparent during development was the cause of the USB hot plug interrupt shutdown. As soon as I plugged in a keyboard into the system, the screen would go black. This error was also quite inconsistent, and sometimes I was actually able to use the system normally. But it would only happen if I plugged in a USB device, and not while using the USB device. This issue seemed to have been caused by the CPU core responsibility. Initially, Core 0 was used for the VGA video processing, and Core 1 was used for the operating system. The operating system was in this case also responsible for handling USB devices. USB communication is also interrupt based, and this turned out to be a problem. Only one of the 2 cores on the RP2040 chip is capable of handling interrupts. This of course can be configured to be any core you want, but I only discovered this later. So now I've decided to use Core 0 for the operating system and the USB device handling, and Core 1 does the video processing. This solution seemed to get rid of the screen turning black as soon as I would connect the USB device. After I fixed this, I was also able to get mouse input working together with keyboard input, and I was also able to increase the clock speed from 200 MHz to 250 MHz. And now that's the point where we're at. So now I also want to have a chance to talk about the future of this project. First off, I want to have SD card support. This is one of the main hardware features that I want on the machine right now, since it would allow for the user to write programs on a machine and execute them on another machine. Besides SD card support, another hardware feature that I want is audio support. For this I'm looking into getting an I2S interface to work. If there are still some plays left, I also want to have a UART communication port on the system. Another feature that I think that would be fun is RGB SCART support, since RGB SCART is quite similar to VGA. This would allow for the Cluatron to be connected to TV sets, in Europe at least. And the final endgame of course is also to have a usable PCB, so other people don't have to build a prototype board like me. Besides hardware features, I also have some software features planned for the future. To start off with the SD card file system navigation. In the future I want to have the user able to navigate the SD card with a Clua shell. I also want to have support for more USB devices, like flash drives and game controllers. There will also be an image editor, which will use a custom format and also be able to output to bitmap. Together with this I also want to have a separate piece of software that is a palette editor, that allows the user to change the color palette of the system. Together with that I also want to have a sound editor and a music editor. This will turn the Cluatron operating system into a true creation suite, kind of like Pico 8. Together with that I also want to have an auto boot sequence from the SD card, which is basically a Lua script that is always called at boot up. In the future I will also have to make sure to have some demo programs that show the capabilities of the Cluatron, which I hope to achieve along with the software and hardware features that I've mentioned before. So if you're interested in this project, then it's nice to know that the Cluatron operating system is a free and open source project, and all the code is located in this repository on GitHub. If you're intending on toying with the source code of the operating system, then I would recommend using a Pi 400, since that is also the development system that I've used connected to my TV to develop this operating system. So if you have any ideas for the development and extra features, then I would love to know on GitHub or maybe here in the YouTube comments. If there are enough people interested in this project, I might just also make a Discord server, but only if I have the idea that there are more than 10 people interested in it. So yeah, that was totally one of the projects I worked on this year. But there is another one. But I'm keeping that for the next video. You probably know what it is.